In this video, I will be reviewing the basic concepts of the photoelectric effect. The photoelectric effect was a phenomenon that was around for about 100 years during the 1800s. It was one of those phenomenon, kind of like the Crookes tube or the bright line spectra, where we didn't have a scientific explanation, and it bothered many classical physicists about why what we were observing did not follow classical physics. Now, just a reminder, classical physics, when it came to energy, said that energy flowed in a continuous way, that you could have an infinite amount of energy, and it acted as a wave through the Thomas Young experiment. Since we're talking about light, what we're talking about is light shining on a metal could emit particles. Now, again, during the phenomenon, we didn't know it emitted particles, but through the cathode ray experiment, we now know that we emit electrons. And these electrons, okay, will flow and hit the other end of the circuit through a partial vacuum here or complete vacuum and close the circuit and create a current. So we knew that a current could be established by light hitting onto the metal, and it would eject negatively charged particles, which we now are electrons, and these electrons would hit this other end of the electrolytic cell and close the circuit. And so why that occurred and how it occurred through observations, again, did not match what we knew. And before we go through this great simulation, which I'm going to use from Phet, it's a terrific simulator, I want to make sure we understand that we knew light had wave properties from the Thomas Young experiment. And then we knew that from Maxwell's unifying equation that there's something called electromagnetism. Light was an electromagnetic wave when he unified electricity and magnetism. And so we know that the speed of light by which all electromagnetic radiation can travel at that speed if it's in a vacuum is made up of wavelengths and frequencies. And there's an entire spectrum, and light is just a small version of that spectrum. Okay, and so this phenomenon was first explained by Albert Einstein, and he won a Nobel Prize for mathematically explaining this phenomenon and explained why classical physics didn't work in explanation, because guess what? There's classical physics is not being upheld here. And to understand what Einstein was doing, he was building or using information that he got essentially from Thomas Young, that light was a wave, from Maxwell, that light's an electromagnetic radiation, okay, and it's part of the spectrum that we've been discussing, and through Planck's constant, to Planck's work. Remember, he was a line fitter that found that these black body radiators had discrete amounts of energy they could accept, that energy traveled in chunks, and these oscillators can only accept these chunks of energy. So energy was quantized, although he didn't really understand exactly what it all meant. He was trying to make sure that he could fit an equation that would explain the ultraviolet catastrophe. But more or less, Einstein, okay, was able to take the idea that these black body radiators, of course, we now know made of atoms, only accepted certain amounts or chunks of energy. So on the shoulders of Thomas Young, Maxwell, and Planck, okay, Einstein was able to take that and explain this phenomenon. So let me show you with this great simulator why this is great. So in any case, what we have is we're going to shoot some red light here, okay? And notice that right here at my cursor here, I'm showing you that there's 761 nanometers. And nanometers is the length of the wave, right? And so the wave is pretty long here because a red light represents a low energy wave, okay? And we should know, okay, that if we take E, right? E is equal to what? E is equal to Planck's constant that we found, that Planck found, of course, times the frequency. Okay? Now we know that red light has a long wavelength. And through Maxwell's equation, okay, the speed of light is by which the limit by which all these electromagnetic radiations can travel, okay, is equal to the size of the wave, which we use as lambda. It's a length, right? Okay, nanometers is a length, and we're going to times that by the frequency. So what do we know, party people, is we know that, let me choose a different color here, that if the wavelength, the size of the wave is larger, okay, if the speed of light is constant, then obviously the frequency has to be lower. Okay, so it was these equations that essentially universal wave equation that Maxwell sort of used. Okay, I mean there's more to it in his equations than that, but essentially that's what we came up with. Planck was able to measure chunks of energy using his constant, and now it was Einstein's turn to build on this. So with red light, we have long wavelengths, and we have what? Because again, the frequency is going to be low because you have long waves traveling, your energy is going to be low. Okay. Now the idea in because of physics, classical physics, that energy traveled not in chunks and was continuous, it made sense that all I need to do is increase the frequency of this light. So I'm going to turn up the light here, and let's get out of this drawing here. So I'm going to turn up this light, and all I need to do is increase the intensity, make it brighter. If I'm making the light brighter, okay, I should be ejecting more. I should be ejecting more and more and more and more of these electrons and get more and more current. And as you can see, nothing happened. As I made the red light brighter by adding more and more energy, hey, energy is continuous based on classical physics, I should be ejecting more and more electrons. You notice? No electrons were ejected. And this goes against classical physics. I don't care what light we start with. Okay, I should be able to turn up the intensity so much that this red light, okay, would be able to eject the electrons. All I gotta do is make it brighter. Energy is continuous. All right, so there was an issue, and the issue was that no matter what the intensity was, we could not eject any electrons. I'm going to lower the intensity. Now, what we're going to do is change the color of the light. Now, notice what's going to happen to the nanometers. The nanometers are going to go down, and if the nanometers go down, that we know that the wavelength is getting smaller, and therefore the frequency is going up, and the energy, okay, is going up. So I'm going to get to, and you notice, I'm at I guess, I'm not good with colors, but I'm at a more yellowy, orangey light, and I'm going to increase intensity some more. And again, classical physics states I should be ejecting some electrons, and I'm not. This goes against the idea. Somehow, I'm not able to eject any electrons. Now, we're using sodium, and we know that sodium is pretty reactive. It's an alkali element, so it should be able to eject electrons easily, but no matter what I do with the intensity, it doesn't go. All right, so what I'm going to do is I'm going to get to what I know is the threshold frequency that was found experimentally. And in this simulation, it's 535. And we can see that I'm starting to eject some electrons. Now, you notice that some electrons are going faster than others. And I'm going to just show the highest energy electrons. We know that those electrons are arranged in sodium in different areas. They're arranged where? Closer to the nucleus and farther away. But I just want to show the electrons for simplicity purposes that are most easily removed, and that's its one valence electrons. So now I am emitting electrons from this light here, okay? And that only occurs when I reach the threshold. If you notice something, as the wavelength got larger, that means the frequency gets smaller, the energy what? Is not great enough to emit any electrons. So in classical physics, it didn't make any sense. If I just made the light brighter, no matter what the light was, I should be able to eject them. But we found experimentally that there was a threshold frequency, or a threshold wavelength in this case, or a threshold energy. And what we know now is that atoms hold on to electrons with different binding energies. Yes, every single element, you know, sodium has a unique energy needed to at least eject the electron, and that's called the binding energy. It's how well the electron holds on, and it's due to the attractive force of the protons. So once I get past the and 535 seems to be the one here, this threshold, I can eject them. Now, I'm going to slow down the intensity all the way down. Okay, now, once I get to the threshold frequency that classical physics wouldn't accept, slowing all the way down would make sense. There's no energy being emitted. And it would make sense that as I increase the intensity, okay, I would increase the amount of electrons being emitted. That, okay, is upheld by classical physics. You're giving off more energy. Therefore, there's more electrons being removed. Okay, you're overcoming that binding energy. Okay, but there's something that is not upheld. If you notice, all of these electrons are going the same speed. Okay, and here's the point I want to make. If you go all the way down to zero, there's no light being given off, and you increase the intensity a little bit. Okay, classical physics states you have a little bit of electrons, but if you increase the intensity, there'll be more electrons. That's great. But having more energy would mean the electrons should be going faster, and that's not the case. So let's go way beyond, okay, the threshold. Let's make the wavelength smaller, the frequency higher, and notice something. Whoa, the electrons are now going faster. And this is something was not explained by classical physics. And the idea was, slow down the intensity. Okay, if I low down intensity, there's not that many what? Let's get some going here. There's not that many electrons being emitted. Okay, if I increase the intensity, there's more electrons. Hey, that makes sense. Light's a continuous wave. Okay, but if you increase the intensity, they should be going faster. And they are not going faster. They're all going the same speed no matter what the intensity is. And so that was troubling to class. I'm increasing the intensity is what? 15%, yet the electrons are traveling at the same speed. Now, how do they figure out the speed? Is they put a retarding voltage here. They made this positive, and they slowed it down, and they realized how much voltage it needed to slow them down. Kind of like the Millikan's oil drop experiment. And this should look a lot like the cathode ray experiment. They're all kind of intertwined, so it's kind of cool. So increasing intensity should increase the speed of these electrons, and it's not. Only when I moved the what? Made the what? Wavelength smaller and frequency higher did the speed increase. Okay, so electron energy and light frequency, okay, were a linear relationship. But look at this graph right here. Look at this graph. It's a linear relationship. The speed at which the electrons flow has something to do with the what? Frequency. But notice something. This right here is the threshold, and every atom had a unique threshold. So how did Einstein make sense of this? Okay, how did he make sense? Going what? How did he make sense of this? Well, the only way to make sense of this is that light traveled in individual packets. Okay, and that individual packets of energy he called photons. And the reason why they went faster with higher energy photons, here I'm in the ultraviolet range, I can stay in the blue, it's going to go a little slower, okay, was that when a photon, in this case a blue, let's make it a blue photon, when a blue photon struck this, and a photon is actually light acting as a particle, and it hits this metal. If it has enough energy, and it does, it ejects the electron. And the extra energy beyond the binding energy is the kinetic energy motion. So you notice when I was at 535, let's go back to what we think is the threshold frequency. Going slower now, because now I'm at essentially the binding energy. If I make this 541. Okay, I'm barely moving. So I'm trying to match the threshold frequency. Now, they're going slower because there's less extra energy. So this photon of light travels as a single light particle. Kind of weird that light acts as a particle. Strikes this, delivers energy based upon the equation E equals Planck's constant times the frequency of this light. And if that little bundle of energy called a photon from light has enough energy to eject electron, it will. Any extra energy beyond the binding energy gives it kinetic energy. So as I make the frequency increase by making my wavelength get smaller, that bundle carries more energy, and that bundle, okay, hits and strikes this, and that extra energy makes it go faster. So the kinetic energy increases with the higher frequency light, lower wavelength light, because there's extra energy per particle, and the extra energy beyond the binding energy. So no matter what, the binding energy sodium for the highest moving electrons, its valence electron, is the same. I'm adding more energy per particle, and therefore that's going to make it go faster. Think of the kinetic energy, the motion of these electrons as the change. Let's say I want to go buy something. Let's say it's shrunken heads, okay? And I need $10 to buy a shrunken head. Well, if I don't have enough energy, lower energy light, each packet of light hitting this doesn't have energy of light. Remember, quantum classical physics states that if I increase the intensity, I should be able to eject. The idea was that no, light travels in packets. So let's say everyone behind me has $9, and the cost of the shrunken head is $10. Well, I don't care how many people line up behind me with $9. Individually, we will not get the shrunken head, which, by the way, is an electron. And therefore, no matter how bright the light is, how many more photons I'm shooting, each individual particle doesn't have the energy. And that's how it works. But if I make the individual particles have what? Enough energy, okay, maybe they should be, okay, I can eject the electrons. I can buy the what? I can buy the shrunken head. So the people behind me now have $11. $10, I get the shrunken head. It's ejected. There's a shrunken head's electron. The extra dollar is used for the change is the kinetic energy. So as I move this to the left, what we're doing is we're still doing what? Removing the electron. We're still getting to the $10, but each person behind me has what? Has now $12, $13, $14, and the extra money is making the electrons move faster. And that's how it works. And to solve the idea that the intensity goes up when there's more electrons, it's not energy flowing as a continuous what? Wave. It's traveling in chunks. By increasing the intensity, okay, I should be adding more electrons, less intensity. Why? There's more people behind me with the proper amount of money to get the shrunken head. Okay, so that's how that works. All right. Now, if I change this out to, let's say, copper, which we know is more resistive, okay, what do you think its binding energy will be? Right? So the binding energy for the threshold frequency for the light to hit this particle and eject it was 535. Now, copper is more resistive. It doesn't lose electrons. That's why we use copper pipes in our house. It doesn't oxidize as easily as sodium. So I would suspect that we would need a higher energy light to reach that threshold. We're still not there. Still not there. Copper resists losing electrons. Therefore, it needs a what? A higher energy light. Okay? And boy, we're really getting this. Like we need ultraviolet light to get it. And there you finally get there. So it's a huge difference. Okay? Increase the intensity. I should increase the number of particles coming off as I add more photons with enough money. So what did Einstein do? And notice the current, okay, being closed here. And this is how photocells work. This is how cameras are able to measure the light. Okay, if I take my phone or my iPad and I want to measure how much light I need, we use the photoelectric effect in a light cell, or we measure the light that way, or we use this to get electricity from the sun. All right, look at that current. So what did Einstein do? Einstein was able to first take a light theory and explain it's acting as a particle. It's acting as a particle. Why? And let's show all electrons in this case. It's acting as a light particle because individual light particles are slamming this. This nice photoelectric effect has options. I'm going to show the photons. Ooh, look at that. The photons are now traveling. That's how light works. And so Planck said that the energy of the oscillators, okay, was quantized. And Einstein said it was the light that was quantized. Okay, and so the light's traveling in particles. And this is the first time we have a duality in nature where light is acting as a wave and it can act as a particle. So Einstein's explanation was that, very simply, that light had particle behavior. And this opened the door for quantum mechanics, because quantum mechanics requires a duality in nature in particle and wave behavior. Unbeknownst to Einstein, who hated quantum mechanics, this opened the door, along with Planck, that there was this energy that did not travel in continuous flow. Traveled in chunks. Planck didn't know exactly what he was hitting upon in his line fitting of the ultraviolet catastrophe. Einstein, okay, was able to interpret Planck's work and say that energy of a photon, okay, travels in a distinct amount of energy. And here comes this very, very important, okay, energy of an individual photon. Okay, it's important you know that is equal to Planck's constant. Here's his energy chunk. Okay, all right, times the frequency of the light. So it's energy of a photon, a particle of light. It's the only way to explain this phenomenon. Okay, hope that helped.